There we go. What does it mean to find the integral? So what are we calculating when we do an integral? We're calculating in the area. Exactly right. So when we look at a graph, like anything, we're always just studying functions. And there's a lot of things you can study about a function. You could look at the function and find its height. You could look at a function and find its slope at a point. Or you could look at a function and find the area. But a line doesn't have an area per se, so we have to add some constraints to it to actually find an area. Where is the area that we're finding? Thank you, Molly. You already answered one now.
What's underneath the line?
Yeah, what's underneath the line? So we're kind of shading straight down from under the curve to trap some area between the function and the x-axis. And how much of that area do we find? Thank you, Colleen. One more person. How much of that area do we find? All the way forever to the right and left? Yeah, just in between two set points that we choose. So I would just choose an arbitrary point A and choose another arbitrary point B, and that would be my cutoff to say, okay, I'm just going to find the area between A and B on the x-axis, trapped between the function and the x-axis, and that's the area that I'm actually calculating. So that's the area that we'd like to find. So that's what it means to find an integral. And in fact, we have a notation for that. We have a long S, and what does that long S stand for?
Sum.
The word sum, right? And what are we summing? Yeah, we're finding the sum of an area. Specifically, what are we summing? What? Well, we're not summing A plus B.
The area between A and B.
We're finding the area between A and B. But to sum something means to take lots of things and add them all together. So what are the lots of things that we're adding all together? The areas of the individual rectangles. Exactly right. We're going to chop this thing into rectangles, and then we're going to add the area of those rectangles together. So that's what we're summing, right? A sum means you're adding lots of individual things together. So what we have here between A and B is a whole bunch of rectangles that we just drew. And then the area of each rectangle we can easily find by calculating the area of a rectangle, which is base times height. And then for each of those rectangles, you find each of the areas and then add all those areas together. And that's what we're summing. So that long S stands for the sum of the rectangles that we drew under the curve. Now, how many rectangles do we want there to be? Infinitely many. And therefore, how wide will each one be? Very small. Yeah, very small. How small? Infinitely thin. And again, there's this idea that we saw in calculus before, that if we wanted to find the slope at a single point, you found the slope between 2 points, and then what did I do to that point? I brought it infinitely close. And then I found the slope between those 2 points. And now what we're doing is we're finding rectangles that are infinitely thin. So that's definitely a main idea of calculus. That was like a psychological shift that humans needed, was to be able to play with this idea of something being infinitely close or infinitely thin. Because I think before the 1700s, if you went to somebody and you're like, hey, so I got these things and they're infinitely thin, they'd be like, whatever you're talking about right now is nonsense. Right? So that was a new idea that people had to get comfortable with. Okay, so we're summing the area underneath those curves, and so each one of those rectangles has a height of f of x. Because remember, f of x represents the height. So the height of our rectangle is f of x, and then the width is infinitely thin, and we represent the width. Okay, let me just draw one. We represent the width of one of those rectangles. Since it is infinitely thin, we represent it by dx. dx represents an infinitely thin quantity. Okay, so if we want to find the area of that rectangle, area equals base times height, we would have dx times f of x. Well, we don't write it in that order. We write f of x dx. So notice now what this notation really looks like. This says find the sum, add them all together, of the area of each rectangle. And what is the area of each rectangle? F of x times dx. For every single rectangle, we're adding them all together. And then from where to where? Starting at A on the left, ending at B on the right. So there's our integral notation. Yeah, there we go. So I think we just unpacked the first question. What does it mean to find the integral? That's what it means to find the integral. Okay, anyone want to add anything else to that? That was a nice little review of what we talked about. How do you find the area under a curvy curve? Oh, I think we just said that. I think that covers it. Ideally, how many slices must you cut the shape into? Infinitely many. How do you read the notation of an integral? Well, we just talked about it. we could read it where you would say from left to right, right? From left to right, find the area trapped between the curve and the x-axis. Now, it's easy to get accustomed to saying find the area under the curve, find the area under the curve. Why is that technically not accurate? Yeah, because technically the function could come down here, and then we'd be finding this area. So it's not that we're finding area under the curve, we're finding area what? Yeah, trapped. I think trapped would be a better word. We're finding the area trapped between the function and the x-axis. Plus, if we technically said find the area under the curve, well, the area under the curve goes down forever, right? So there would be, the area would be infinite, and then the question would be silly. So we're finding the area trapped between the function and the x-axis. Finally, when is the area positive and when is the area negative? Which one of these areas is positive and which one of these areas is negative? Yeah, above the x-axis is positive, below the x-axis is negative. This is a convention, but it also makes sense because after all, width, you know, this width, this infinitely small width is positive. Width is always positive. But if you want to read the height, this f of x right here, that height is f of x. And in this case, that height would be a positive number, like say positive 5. But if I found the height right here, what would f of x be right here on the x-axis or on the y-axis? That would be a negative number. That'd be like -4. Therefore, for this rectangle, that rectangle down there, your f of x, your height would be a -4 and your width would still be dx. And when you multiply a positive times a negative, you get negative. So I forget which one of you asked, does the formula automatically tell you that this area is negative? The answer is definitely yes, because the f of x that you're using to calculate the height of that rectangle is automatically negative because the height is negative. Because you read f of x off the y-axis, which is down here, which is negative. Does that satisfy your question now? Sweet. All right. Okay, well, there we go. So, you know what? My goal is constantly to make sure that we develop a strong conceptual understanding of what on earth we're talking about. And then we have to develop all the nitty-gritty skills to actually do these integrals. So I hope that that all made sense. I realize this is just our second day looking at it. Yeah, that's it. I'd like to show you that website one more time, Shodor. Shodor. What I do is because what I'm saying is you're all going to want to go home, in case you didn't already. Well, obviously you want to go home. But I mean, you want to go home and look at this website, Shodor, and then you type in integrate, as in integrate. And you can go there and play around with this website. It's pretty cool. So you can just choose any graph you like. I was doing 25 minus x squared because it gives a nice, there we go, a nice little curve there. You can see the rectangles. What I'd like you to see right now, I'm going to go from -10 to 10. How about that? Ooh, see, now look what they're doing. Do you see what's happening? You've got the rectangles above the x-axis, but you also have the rectangles down below the x-axis. And as the number of partitions, now notice they use the word partition. We were using the word subdivision. We were using the word rectangles. But rectangles, partitions, subdivisions, they all mean the same thing. It means the number of rectangles. So as I increase the number of rectangles, my calculation of area becomes all the more precise, and you'll see that the decimal value is honing in on one particular value. And you'll also notice that in this case, what's the area? Negative. Why? Yeah, because you have more negative area down below than you have positive area up above. Now, area, and then we canceled some of it out with a total amount of positive area. So that number that we see right there, the -167.2, is not the total amount of shaded area. It's the balanced out amount of area once you take the positive away from the negative. Okay, what did I want to show you here? Oh yeah, so if I take my number of partitions back down, so you can just look at the, in fact, we're going to go from 5, and we'll bring this down a little more. Okay, we talked about where those rectangles go. So first of all, folks, just by looking, look at one rectangle. Can you tell me, is this a left-hand Riemann sum or a right-hand Riemann sum? Yeah, left hand. Why left hand? Yeah, because if you look at the rectangle, the left corner of the rectangle is touching the blue line, Not the right corner. I mean, just look at that right corner. It's not touching anything. So the left-hand corner of the rectangle is touching the blue line. What about over here? Is it still true? Is the left-hand corner touching the blue line? Yeah. So this is a left-hand sum, and you can see from my drop-down menu, I have a lot of choices of Riemann sums I can do. I can do a left-hand sum. I can do a right-hand sum. Now the right corner of every rectangle is touching. So what else could we do besides making the right corner or the left corner touch?
Both.
We could try to do both. That could be, I'm not even sure what that means, Josh, but yes, fine answer. We could try to do both. I'm going to show you the drop-down menu, and you're going to look. We could do a midpoint where the middle of the rectangle touches the blue. That probably seems better, doesn't it? Like, why are we even messing around with the left and the right hand when it so obviously is undercutting it? Whereas if we do the middle, a little bit pops out, a little bit pops in. So you have some overestimate, some underestimate. This obviously seems a little better, especially because, as I said, when you zoom in at one particular point right there, that blue line, if you zoom in infinitely close, the blue line is essentially a straight line. And then the amount popping out and the amount sticking in is the same. That would be in theory, if you zoom in far enough. So yeah, the midpoint one seems pretty good. What about a trapezoid? Whoa. Well, now maybe you're like, well, why are we even messing around with rectangles when we could just use a trapezoid? I mean, first of all, is there any overestimation? No. Not in this case. And it looks like a pretty good fit. The only bummer is, what kind of shape are we looking at?
Trapezoids.
A trapezoid. And what's the formula for the area of a trapezoid? It's a little more complex. I mean, a rectangle is base times height. A trapezoid is 1/2 b1 plus b2 all over, or times h. Not nearly as nice, right? There's a little bit more computation to do, even though it obviously does a better job of approximating the shape. You could also do an average sum. Well, actually, I have no idea what that's doing. And an upper sum, not sure what that means either. Okay, I'm not sure what the last couple ones mean. In any case, I hope you want to go home, play around with that. You can type in other functions like sine of x, and then you could see something like that. There we go, that's nice. So now we're finding the area trapped between a sine curve and the x-axis. And then you could, okay, that's about as good as I can get here. Let's go from 0 to pi. There. So that is it looks like a parabola, doesn't it? But it's really the sine curve. And we're finding the area underneath that sine curve. And here's just, well, darn, I can't get any better. Oh no, I could do the midpoint sum. It turns out that the area underneath one hump of a sine curve is exactly 2. Yeah, it's going to be 2. If I could do infinitely many rectangles infinitely thin, isn't that weird? That's crazy. What? That's weird. Because honestly, look at a sine curve. A sine curve goes up and then down, and it only goes up as high as 1, and it cuts through at pi. So we have this humpy shape right here, and the width of it is pi, and the height of it is 1, and it turns out the area inside of it is exactly 2. Isn't that surprising? These are just little surprising nuggets that we learn when we study calculus and integration, that certain answers come out to be really, really clean and really, really nice. All right, well, that's probably it. Well, we could just talk all day, couldn't we? Okay, so here we are. That's the wrong calendar. I'm going to go back to the right calendar. I tend to have a problem with calendars. All right, today is March 21st. This is all wrong. Yeah, that's all wrong. I apparently did not put a correct. How could I not put a correct calendar on here? I didn't. I'm so sad. All right, well, I have no correct calendar to show you. But that's okay. I think we all know today's Thursday. All right, so today, Thursday the 21st, we're going to continue working along through chapter 3. And how far did we get? Are we on number, I think you all finished number 4 on your own, and now we're on number 5? Yes. Okay. Before we dive in here, does anyone need anything? Do you need a packet? Do you need the notes? Do you need emotional support? All right, so here we go. It says estimate the area under the graph of f of x equals 1 over x plus 3 over the interval 3 to 6 using 4 approximating rectangles and right endpoints. Then do the same procedure with left endpoints. Tell you what, we can just do that for now. Right endpoints. Let's just focus on doing the right endpoints. So we're going between 3 and 6. What do we do first? Sometimes it can be overwhelming. What should we do first? What's that?
Mark 3 and 6.
Yeah, mark the 3 and 6, right? I mean, we got to start somewhere. So let's go ahead and mark the 3 and the 6. And I'm going to mark it all the way up because this is the left hand, and then this is the right hand. So I'm going from 3 to 6. And in fact, just for fun, let's find out what the answer is. Like, we can go ahead and use the integral notation. We're going from 3 to 6 of this particular function. And I can go ahead and put in the function. From 3 to 6, it's 1 over x plus 3. And you know what I can do? You know what you can do? You just type it into Desmos.
Oh.
Is this exciting or what? You can just go over to Desmos. Not Shodor. Shodor is only giving approximations. We don't want an approximation. I mean, technically, we could do an approximation. Watch this. We could do 1 over x plus 3. We could go ahead and integrate from 3 to 6. And how many rectangles do we want? 4? That's what they asked for? 4? Boom! Just did it. And what do they want? The left hand? The right hand? Boom! There's the answer. Everybody write it down. 0.385353. Now keep in mind, this isn't cheating. Well, I mean, it's only cheating if you go home and you're doing your more homework and you just go to Shodor and you type in the answer, you're like, done. Right? This isn't cheating, this is confidence building. This is figuring out what the answer is so that when you do go through all the long steps of finding your answer on your own, you'll have immediate gratification knowing you did it right. Of course, you'll have that gratification since you type it into more and it tells you if you're right or wrong. But this is really nice because look, it's kind of telling you what it should look like. Now we have a nice visual image of what this thing is supposed to look like. All right? Furthermore, as I said, I can now go into Desmos. You have to click on the little keyboard down here, and you have to go into Functions and go on over to Miscellaneous, and then there's the long S. Does everyone see it? The long S. So now I can do an integral from 3 to 6. Oops. 3 to 6 of the function 1 over x plus 3, and you do have to type dx. And there's the answer, 0.4054. So that's the actual answer. Now you'll notice it did not show me the graph. Okay, it's not actually going to graph it and shade it. Your TI calculator will do that for you. Your TI calculator will graph it, shade it, tell you the answer. But Desmos just tells us the real answer. So the real answer is 0.4054, whereas you all know the approximate answer was what, 0.38? Okay. All right. So now that we all know what the answer is, we all know what it looks like, we all know what to expect, now we can try it. So it says use 4 approximating rectangles. I gave you a formula yesterday that said the width of our rectangles is the total width of the integrated area divided by the number of rectangles, right? So the total width from 6 to 3, 6 minus 3 is 3, and the number of rectangles we're using is 4. So the width of each rectangle should be 0.75. So that means in order to draw our rectangles, we're going to have to kind of find the approximate location. So 3.75 would be between 3.5 and 4. You know, $3.75 would be right here. So it's 3.75. So that's one rectangle. So now what's 375 plus another 75 cents? Yeah, 75 plus 75 is 150. So 375 plus another 75 cents is 450. So there's our next rectangle. You notice I'm not drawing the rectangles yet. I'm just drawing the lines to show me where the subdivisions are. And then 450 plus another 75 cents would be 525. And then 525 plus another 75 cents would be 6. So does everyone see how I kind of worked my way across this axis, finding the location of the subdivision numbers? First, I calculated how wide each rectangle would be, and then I just started adding 0.75. Leapfrogging my way over. Okay, so now I have, indeed, 1, 2, 3, 4 rectangles. And what do we want to do? We want to do the right and... No. Does everybody have the lines drawn? I don't want to go too fast. I'll make sure that everybody has their lines drawn. Okay, super. Hey there, JR. We're using the 3.1 packet, which I need to give you. Does everybody have the 3.1? I think so. Okay. Okay, so now what? The right endpoint. So might as well start off the far right. And let's draw our rectangle. So this rectangle, straight across. And then you go this line to here, straight across. It's very subtle, right? And then this, the top of this one, straight across. And then attaching to this one, straight across. So does everyone have 4 nice little rectangles? Draw your top lines. Your top lines should be underneath the curviness of the line there so you can see it. Right? So you still need to draw those top lines in on your rectangles to make them rectangles. Okay, well at this point, we have our rectangles. Now it's just basic geometry. We just need to find the area of each rectangle and add them all together. So how wide is each rectangle? Do the easy part. Yeah, the width of each rectangle is 0.75. That's kind of nice. So we know all the widths are just 0.75, which we got from our original calculation of how wide is each rectangle. Well, now we need to know how high each rectangle is. Fortunately, we're all experts in knowing how to calculate how high a function is. So how tall is the function at this point right here? What's that? Well, that's true, 1/9. You already plugged it into the function. Tell me more abstractly. How tall is a function? What function represents the height? F of x. So f of x represents the height, so this height is f of 6. Right? That's the height of the function right there. Therefore, this rectangle is f of 6 tall. And how tall is this rectangle? F of 5.25? We're just going to write it in abstractly at first, because I want you to see this as this notation. How tall is this rectangle? F of 4.5? And how tall is this rectangle? F of 3.75. And what about this height? Do we use that height? We don't use that height. When would we use that height? If we were doing the left hand. And if we were doing the left hand, we wouldn't use that height. Okay, so doing great. We now have the height of all 4 of our rectangles. We have the width of all 4 of our rectangles. So now we just have to go calculate those values. This is a little awkward, but for the lack of space, I'm just going to show my work above it. So what is f of 6? The function is 1 over x plus 3. So it's 1 over something plus 3. What am I plugging in? 6. So that answer is 1/9. It's a little strange I'm working up. We don't normally work up. I don't think I know even too many cultures or languages that work up. What language does write upward? I think there's an Asian language that writes upward, or is it or they write down? But it goes from right to left. Oh, Arabic does? Sure thing. Oh well, in any case. Okay, so now how about this one? We're going to plug 5.25 into that. So it'd be 1 over something plus 3. So I'm going to plug in 5.25. And therefore that height is 1 over 8.25. That's the height of that rectangle. That's the height of that rectangle. So then I have 1 over 4.5 plus 3, which is really 1 over 7.5. That's the height of that rectangle. And then I have 1 over 3.75 plus 3, which is 1 over 6.75. And that's the height of that rectangle. Yes, sir. The 0.75, this is a formula that we saw on Tuesday, where the width of each rectangle is found by calculating the total width of the interval that you're doing. So we're doing the interval from 3 to 6, and if you subtract 6 minus 3, you get 3. So the total width is 3. Again, 1, 2, 3. Total width is 3. And then you're dividing by the number of rectangles that you want. We want 4 rectangles. So 3 divided by 4 is 0.75. And that gives you the width of each rectangle. Sarah, thank you so much for asking that question. It's really important. I don't want any of you sitting there with a question on your mind. Unless it's about life in general. Colleen.
What did you say? You said you want 4 rectangles?
Yeah, they said that right in the beginning. They said over the interval 3 to 6 using 4 approximating rectangles.
Oh.
Yeah, that was in the problem statement. Okay, well, folks, we're ready now to just find the sum. Remember, sum, that's why we use this long S. Let's find the sum of all 4 rectangles. So my sum of base times height for all 4 is going to be, so I'm going to do the first rectangle, 0.75 times 1 over 6.75, plus 0.75 for the second rectangle times 1 over 7.5. And then plus 0.75 times 1 over 8.25, plus the fourth rectangle, 0.7 base times height, 1/9. Now again, notice that for each of these, that's base times height, that's base times height, that's base times height, that's base times height. Writing down more is always better than writing down less. Like, you might have just watched me write base height plus base height plus base height plus base height 4 times. You're like, OMG, I'm not writing that down. But it adds clarity. It reminds me what each of those things are. Now, as before, I can factor out my 0.75 so that I simply have 1 over 6.75 plus 1 over 7.5 plus 1 over 8.25 plus 1 over 9. And that is the area under the graph over the interval 3 to 6 using 4 approximating rectangles using right endpoints. Let's see if we got the right answer. Huh, the right answer. We're getting the right answer, and I hope we also get the right answer. So you want to be really careful here. I would add up the inside first and then multiply times 0.75. Like, unless you're really taekwondo with the parentheses, if you just do 0.75 times that, plus that, plus that, plus that, your calculator might think that you just may multiply those two, and then just add all those in. So do the parentheses first. After all, PEMDAS tells you to do parentheses first. So type in 1 over 6.75 plus 1 over 7.5 plus 1 over 8.25 plus 1 over 9. So I have all of that sum. So that's 0.75 times 0.5138047. And then times the 75 cents, and I get 0.38533. And oh my goodness, was that not the answer that we saw from Shodor? Shodor. I don't know that answer. Okay, now we just did a ton of work, right? Your paper should be giddy with work. And now the instructions say, now do the same thing with the left-hand side. And you're like, oh man, I need a whole other graph. But do we even need a whole other graph? Do we even need anything? No. All we need to do actually is find this height. So I already know that that's going to be f of 3, which is 1 over 3 plus 3, which is 1 over 6. And then I could use a different color pencil and draw in my left-hand rectangles. Left-hand rectangles. Left-hand rectangle, left-hand rectangle. And now, without even, just labeling the fact that now I'm doing the left-hand rectangle, I could even just go ahead and write 0.75 times, and I'll just write my 4 heights above my left-hand rectangles. No real additional work is necessary. I'm just going to go ahead and write down now that I'm doing the sum of 1/6 plus 1 over 6.75 plus 1 over 7.5 plus 1 over 8.25. And now that's going to give me the sum for the left-hand approximation. You'll notice here that we did what we did in the previous problem, that now we're using the first chunk of the data, ignoring the last data point, whereas what we just did first was ignoring the first data point and summing the rest of it. Right? So like whenever you do a left versus a right, you're always just adding up all the y values, either ignoring the first data point or ignoring the last data point. So what does that give us? 1/6 please. My final computation was 0.42702. The right-hand sum, 0.38, the left-hand sum, 0.42. Remember, we talked about the squeeze theorem. The squeeze theorem states that the real answer is going to be less than the over-approximation, but more than the under-approximation. And for any given problem, as you let the number of rectangles increase to infinity, the real answer will get squeezed right in between. And in fact, as you let the number of rectangles go to infinity, the overestimate will equal the underestimate because you've squeezed the real answer in between. So right now, we know that our real answer is between 0.427 and more than 0.385. So what could we do to just kind of have an off-the-cuff answer? Yeah, we can just take an average, right? So 0.427 plus 0.385, and that's 0.812 divided by 2, and that tells me that approximately the real answer is 0.46. Now, should we actually have any confidence in this answer? I mean, it's close, but then again, these are close. But this idea of just averaging these two, it's kind of trash. It's not real, you know, don't actually do that. What we really want to do is let the number of rectangles increase to infinity. That will do it, the trick, right? If we just let the number of rectangles go to infinity, these two numbers will get closer and closer together, and in fact, they'll be equal to each other, and you'll know, therefore, that that's the real answer. But did anyone write down what Desmos said? It was 0.40. What was it? Still got it here. Desmos said 0.405. So not bad, right? Not bad at all. Okay, well, I will certainly give you one of these on the test. Because it's just good, detailed, careful work, right? Like, no employer in the world really is going to say, like, hey, can you do a Riemann sum on a graph? But every employer in the world is going to say, can you do some really slow, careful, detailed thinking and work your way through a mess of a problem and get to the end? Every employer wants that. So go home, practice this problem. You know, it's certainly on your homework, on the more homework. So, you know, draw it out, print it out. Even better, print it. You know, I don't know if any of you are printing the homework from more, but you can just click print, and we'll print it out for you, and then you'll have the graph and you can draw on it. Because otherwise, it's kind of tough to do a problem like this on paper without a graph. The graph is really helpful. Anybody have any questions? Henry?
So, for like formatting the information in this problem, you have there like a left colon, and you did the calculation, and then I can do a right colon.
Well, this was my right colon. The first one we did was right.
There's no like notation for the integral to dictate whether it's doing right or left, right?
You are correct. The actual notation right here, the actual integral symbol, implies infinitely many rectangles.
Yeah.
And if it's infinitely many rectangles, it doesn't matter if it's right or left, because they both give the same answer.
You definitely want us to just let you know.
Yeah, like which one's right, which one's left. Yeah. Yeah, and I mean, part of me thinks, gosh, you know, I don't need to be mean and make you do both. But the fact is, by the time you finish doing all the hard work to get one of them, the other one's so simple to just, you know, notice what the pattern was and fill in the other data point. You know, because what did we really do? We took out this data point, the 1/9, and we put in the 1/6. But otherwise, all the other data points stayed the same. So it's not too hard to switch from the left to the right now. Okay, another question? What's up, Molly? One? JR? I know, JR, you must have some questions because you weren't here the other day.
Yes, actually, when you were finding the n weights to the left, you're going from 1/6 to 1/7.
Yes, so when you're doing, so you look at each rectangle and you go up the left-hand side to where the rectangle meets the function, and that's the height of that rectangle. Okay. Wait, was that actually your question?
Yeah.
Oh, okay, yeah. Okay, well, let's see here. I think that's, oh no, we might have, well no. That was it for the tricky ones, folks. That was it for our practice of actually drawing in Riemann rectangles. So let's go ahead and move on. Unless anybody else had any questions? Thank you, Eric. Thank you. Elaine, Josh, none?
Watch the video.
Oh, you did watch the video? Wait, you said not super interesting? Oh yeah, it is very, very tricky stuff. Okay, well then, here we go. The next few problems are fortunately a little more conceptual, not so much nitty-gritty drawing of rectangles and calculating heights and adding them all together. So let's take a look here. So take a look. This problem says, to find the blue shaded area, we would calculate what? So first of all, if we wanted to find the blue shaded area, we could do that immediately using geometry, right? I think everybody would feel comfortable doing this problem in geometry. Now, how would you find the area of the blue shaded area? Would you do a trapezoid? You'd certainly do a trapezoid. Everybody do it with me. If we wanted to find that trapezoid, remember it's 1/2 base 1 plus base 2 times height. Now, in this case, you have to turn your head, right? Trapezoids, we typically think of the bases being parallel. So this is actually base 1, base 2. That's the height. So we would turn our head and we calculate the area of that trapezoid. So base 1 would be, well, what? How tall is that? I'm going to say 3.75. And in fact, I actually think it is 3.75. How can we prove that to ourselves? Well, you could do all sorts of things. Notice what the slope is, folks. What's the slope? Take a look at this point compared to the next whole integral point. It's down 1, right 4. So down 1, right 4, that's negative 0.25. That means the height is decreasing by 0.25 every time you move over 1 block. So, and because I can just change negative 1/4 to negative 0.25 over 1. So that means down a fourth, right 1, down a fourth, right 1. So down a fourth, right 1, that puts us at 3.75. So it really is 3.75. That's not just off the cuff. Let's just call it 3.75. Okay, so our B1 is 3.75. Therefore, what is our B2? If you go down a quarter again, you're at 3.5. If you go down a quarter again, you're at 3.25. So now that B2 is 3.25. And what's our height? We're going from 1 to 3, so how wide is that? Yeah, 2. You can either count it, 1, 2, or you can just subtract, right minus left. 3 minus 1 is 2. So what do we have then? 1/2 of 7 times 2. So half of 2 is 1, so the answer is 7. So we now know that the answer to this problem is actually 7. Now, they didn't actually want us to calculate the area. They just said, to find the blue shaded area, we would. But I wanted us to actually do it just to practice and have fun with geometry. Now, you don't have to do a trapezoid. What else could you do? What could you do instead of a trapezoid? Yeah, you can do a rectangle and a triangle. And again, practice some geometry. How tall is my blue rectangle? Still 3.25 and a width of 2. So I immediately know that my blue rectangle has an area of 3.25 times 2, which is $6.50. And then what about my little teeny triangle? How tall is it? 0.5. So 0.5 times the width of 2, and a triangle is 1/2 base times height. So 1/2 times 1/2 times height. So that's half times 2 is 1, so half. So that area is 1/2. So if that area is 1/2 and that area is 6.5, you add them together, what's 6.5 plus 1/2? Still 7, which was the answer we previously got. Okay. So again, I'm just encouraging us to think geometrically because that is what we're doing. Keep in mind, ancient cultures could have calculated areas by doing exactly this. You break it up into shapes, right? But our job as calculisticians is to find the area of curvy shapes. And the only way to break a curvy shape into a shape is to make that shape an infinitely thin rectangle, right? Like this one, we actually were able to break into a triangle and a rectangle, but if it's curvy, the only shape that will work is an infinitely thin one. And that's why it requires calculus. Okay, so now moving on, we want to find this, this integral here, right? So what's our a value? Yeah, how far to the left are we going? You might even label it a to b. We're going from a to b. So a is 1, b is 3, f of x is that function. Well, what is that function?
1.5.
Yeah, we know the slope is just a straight line, so we can find that function real quick. The slope was down 1 right 4, so that's down 1 right 4x, and the y-intercept was 4. So there we go, that was our function. And we already know the area because we did calculate it, so it turns out we did have to calculate it. 7. So we did an integral. I mean, we kind of did an integral. And actually write it down now. What we just found was that from 1 to 3 of negative 1/4 x plus 4 dx equals 7. That's what we just found. Definitely write that down. Because that gives you a nice example of seeing what the notation looks like and knowing what the answer is ahead of time. How could we confirm our answer? Well, we got Desmos. So now that I know the actual function, I'll come over here to Desmos and just type in go negative 1/4 x plus 4. And we're going from 1 to 3. And there we go, the answer is 7. So it all worked out, and Desmos is a really nice way to check your answer. I'll put it in. So this problem, the instructions are wrong. What I want us to do is use 37 approximating rectangles and do it from the left hand and the right hand and compare the two answers. Totally kidding. I was trying to make it sound terrible. 37 rectangles, really? Everybody look at this really closely. Where are we calculating the area from? We're calculating the area from where to where?
3 to 7.
From 3 to 7. So everybody draw in 3 and draw in 7. And I want you to calculate the area. You have 10 seconds to calculate the total area trapped by the curve.
0.
Hold on a second there. I want you to calculate the total area trapped between the curve. Keeping in mind that the area above is positive and the area below is negative. Is what's that? Yeah, that is a straight line. It is a straight line. It's a linear mx plus b. So the slope is 5 over 1x, and then the y-intercept is negative 25. So what do you notice about those two shapes? They're triangles, and they are, in the language of geometry, congruent. They are congruent because the width of each triangle is 2. The height of each triangle is 10. And so that width is 2, and that height is 10. And therefore, the area of each triangle is 1/2 base times height, 1/2 times base times height, which is 10. So this is a positive area of 10, and this is a negative area of 10. And therefore, the total area is just 0. And the total area is 0. So that was a little bit of a trick question, right? Wouldn't that be nice to see that problem on more?
Yes.
It's like a little gift. Okay, doke. That's that one. There we go. Now, how about that next one? This one, number 8, is a circle. Well, at least does it look like a circle?
It's a semicircle.
Yeah, it's a semicircle. It's half of a circle. And this says, evaluate the integral below by interpreting it in terms of area. In other words, draw a picture of the region and the integral represents, and find the area using geometry. Now, first of all, folks, you'll notice that that graph right there, that's from Desmos. I did that for you. I gave that to you. This problem on more won't show you a picture. It'll just show you that integral. So because I was a pal and I gave you all the graphs throughout this whole packet, like all the graphs in this packet, I pasted in there so that we would all have it together. When you're doing your homework online, they don't give you a graph. They would want you to go to Desmos and look at the graph. So for instance, that one, there's no picture. You'd have to go graph it on Desmos. And like that one, there was no picture. You'd have to go look at it on Desmos. That was there. That That one was Desmos. I put that there for you. Okay, yeah, so I put some of those pictures there for you. So let's look at this one right here. All they would have really given you in this problem is that funky looking integral. So what you would have to do then is go graph, not the integral, but the square root of 2 squared, which is 4, minus x squared, and look and see what that is. And you'd look at it and you'd say, oh, well, that's half a circle. Right? And then what are they asking us to find the area? From where to where? Yeah, from -2 to 2. So they want that whole area. They want that whole area right there. There. Well, I wish I could cover up the bottom half. Just pretend you don't see the bottom half. So, oh, I can do it. There. That's the area that they want. So we can calculate that integral without doing calculus because we know the formula for the area of a circle. And what is the area of a circle? The formula for the area of a circle. Pi r squared. So we would say the area of a whole circle is pi r squared. So if this was a whole circle, the area would be, what's the radius? 2. So the area of the whole circle would be 4 pi. So what's the area of half the circle? Yeah, half of 4 pi or 4 pi over 2. And so the actual area is. And that's it. We're going to finish this packet before we take a break. Now, furthermore, could I go ahead and check that on Desmos? I already typed in my function. I'll go ahead and do my keyboard. Get the integral symbol from functions, miscellaneous, integral from -2 to 2 dx. And the answer is 6.28. Is that 2 pi?
Pretty much.
Yeah, 2 pi is 6.28. There you can see I just verified my answer. So, what they're kind of getting at in this unit is showing us that we're able to use geometry in a lot of problems. But this notation that we've just developed, the integral notation, which we'll learn how to solve soon, tackles the rest of the problems where geometry would not be helpful. Any questions about that? All right. 2 more. Here we have a nice little picture. This one is in the more program. They would give you this. And they're saying evaluate the integral below by interpreting it in terms of area as a figure, and the areas of the labeled regions are, so now go ahead and label all these in. Area 1 is 8. Area 2 is 3. What should I write down? And -3. Area 3 is 2. And just for a good measure, I might as well write plus up there, just so we don't leave anything for assumption. And area 4 is 1, that's -1. So good practice to actually write plus when it's plus and minus when it's minus. Okay, so then what is, they're saying calculate this integral, which they're calling v. I don't know why they're calling it v. But find the area from 0 to 7. So what's the total area from 0 to 7? You got it all up. Yeah, 8 plus 2 is 10, 10 minus 3 is 7, answer 7.
Isn't it also
We're just going from 0 to 7.
oh,
Yeah. If you did go from 0 to 10, then yeah, it would be the whole lot. Okay. Well, I hope that we've all developed a little more intuitive understanding of both the notation, how to read from left to right, area on the curve, positive up top, negative down below, and chopping things into rectangles and using geometry to help us out, and using Desmos to find the answer, or Shodor to find your approximating rectangles. So we just have one more here, and it says, given the function graph below, evaluate the definite integrals. So they give us a couple to do here. Yeah, good point. So we haven't gotten there yet. If you do an integral, see, this didn't make sense. They kind of introduced the notation beforehand. If you do an integral without the numbers, that's called an indefinite integral. And if you do the integral with the numbers, then that's called a definite integral. This is ahead of us. We're not here yet. If you just do an integral without the numbers, all you're really doing is doing an antiderivative. So the antiderivative as opposed to the derivative, and you get a formula as the answer. It's just going to be an equation. Whereas if you do a definite integral, then you actually are calculating a genuine area. That doesn't need to make sense yet because we didn't get there. But yeah, they seem to have introduced that notation ahead of time. These are definite integrals because the numbers are there. We're actually calculating the area, not a formula. So how do we find the area from 0 to 1? From 0 to 1, it's trapezoid. So you can either do a trapezoid or you can do a rectangle and a triangle. And you're just going to find those areas and add them up. So the rectangle is pretty easy because it's 1 by 1, so that area is 1. The triangle has a base of 1 and a height of 1, so 1/2 times base times height is 1/2. So that's 1/2. So I just calculated the area of the rectangle, the area of the triangle. That's the total area. 1.5. The area is, it's not 1.5.
Negative.
Negative 1.5. Very good. So that answer is negative 1.5. Very good. And what we just found, I'm going to screw it in now, is that. We found that that area right there is 1.5. Oh, that looks like 1 over 0. Okay. Now how about the total area from 1 to 7? Now we get to do all the rest. So you just chop it up as you see fit. Doing triangles. That would be a triangle, I think. This would be another triangle. And then you'd have a square. Right? You just find the area of each of those and add them all together. Keeping in mind that that little triangle is negative. I'll start working out here so you can check your answer. And I'll write my answer inside.
It's negative because under the axis.
Right, it's negative because it's under the axis. Absolutely. And it's negative because the function, the height is negative, because the y value is negative. Therefore, the area is negative. All right, so the time is 11:56. We'll come back at 12:06. Refreshed and excited and ready for more. Yes. Okay. Yeah, definitely watch the video. Do you know where the links are? Okay. Alrighty. Everybody has their 3.2 notes? Is that done? I will take the deafening silence to mean yes. Everyone has it. So we have developed an understanding of what an integral is, how to do a Riemann sum, what the notation looks like. And right now we're ultimately just calculating an area. A very basic concept. You all know the etymology of the word area? Etym Online is one of my all-time favorite websites. Etym Online is an online etymology dictionary. Area means a vacant piece of level ground. Boy, isn't that exciting. That's the original use, going back to Latin, a vacant piece of level ground. And so with area, we're talking about, how much land you have. Because back in the day, that was really important. Because if you had land, you could plant crops, you could grow agriculture, you could build a castle, you could own things, right? So area is how much land you have. All right, so all right. Here's my essential question. What relationship exists between the derivative and the integral? Okay? What relationship exists between the derivative and the integral? Because keep in mind, that's what our class is. Calculus is differential calculus, that is derivative calculus, and integral calculus. So these are the two parts of calculus. And as we've already shown, they both have to do with infinitely small things. So when we did derivatives, we were finding the slope between 2 points that were infinitely close. Yes, Jerry? Can you come in? You didn't get the 3.2. So in derivative calculus, we were finding the slope between 2 points that are infinitely close. So that's derivative calculus. Whereas in integral calculus, we were finding the area of a rectangle that is infinitely thin. Both of these are paradoxical because if I find the slope between 2 points that are infinitely close, 2 points that are infinitely close are actually the same point. If you have 2 points that are infinitely close, it's actually the same point and you get 0 and 0. So there's a paradox there. If 2 points are infinitely close, you find the slope, it's really 1 point, so there's no slope. Well, that is the formula we give you indefinite. Undefined is what. Whereas if I actually find a rectangle that's infinitely thin, what's the area? A single infinitely thin rectangle is just a line and there's no area. So both of these are paradoxical, and yet the fun thing about the integral is that if you have one infinitely thin rectangle, the area is 0. But if you have infinitely many infinitely thin rectangles, the area is something. Right? So that's weird. So what do they both have in common? They're both studying something that's infinitely small. 2 points infinitely close, one rectangle infinitely thin. So that's why they're both calculus, because we're dealing with infinitesimals. Have you ever heard that word? Infinitesimal. We're We're dealing with infinitesimals, which at the time this all came about, in the late 1600s, early 1700s, people said that's just make believe. You know, there's no point. Why are we even talking about this? It's not a real thing. Okay. So now let's look at specifically. Okay. What relationship exists between the derivative and the integral? So let's say that I did want to find the slope between 2 points that are infinitely close. What we did there was we said this was x and this was x plus h. And then we did f of x plus h minus f of x all over h. And if we consider what that fraction is, what the units are, f represents the y-axis, that's your change in y. And the denominator, you know, looking at the slope formula, the denominator is your x-axis, therefore that's your change in x. So when we do a derivative, we're fundamentally looking at a quotient, a fraction, delta y over delta x. That's what we do when we find a slope. So what about area? When we look at area, we have the area of a single rectangle, and that rectangle has a width of delta x, that's how wide it is, and it has a height of delta y, that's how high it is. And then the area, which is base times height, gives us delta y, well, I reversed the letters, delta y times delta x. Right? How does everybody feel about that? So in a derivative and an integral. So what relationship exists between a derivative and an integral? Yeah, one of them is multiplication, one of them is division. Right? When we think about inverse operations, plus minus, multiply, divide, square root, we also have a derivative integral. And these are all called inverse operations. And what do inverse operations do? Yeah, they allow you to go back and forth. They cancel each other out. If you just look at a real basic algebra problem like x plus 5 equals 10, how do you solve for x? You minus 5. And why do you minus 5? Because it cancels it out. So inverse operations cancel each other out. They're opposite operations. The derivative and the integral are opposite operations because literally one is multiplication, one is division. So that's the relationship that exists between them. That one of them is division, one of them is multiplication. And therefore they're opposite operations. Just like multiplication and division are opposite operations. So that's one thought. That at least intuitively, we want to have this idea that a derivative and an integral are opposites. And in fact, that's why we call an integral the antiderivative. The antiderivative. So if this is the derivative, then the integral would be the antiderivative. It's its opposite. Okay, so that's just kind of our lead-in question there. So the big idea, the integral is the antiderivative. So how do you do the antiderivative? It's a fun question. And in fact, I'm going to lead into it with the idea of algebra. We all take out a sheet of lined paper. I want you to do a fun algebra exercise with me. This is a really good exercise. And if you've never seen algebra from this perspective, I think it'll really tickle you pink. Right? Tickle you pink, that's a phrase, right? What does that even mean anyway? You're tickled so much that you turn pink in the face because you're out of breath? Because you're laughing so hard, tickle you pink? Okay. So let's just say that you had an algebra problem, and the algebra problem was 3x plus 1 square rooted divided by, let's say, 4 plus 7 equals 8. First of all, does anybody know the answer off the top of your head? I go, yeah, x is 11. Well, I hope you don't know the answer off the top of your head. Because the point of algebra is not to guess. The point of algebra is to follow a specified series of algorithmic steps. They get you the answer. So here is how algebra works. You tell the story of x. And my goal here is to really impress you. You're like, wow, this is fun. So I want us to look at the x, just look at the x variable, and we're going to use PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction, to tell the story of what's happening to x. So what's the very first thing that happens to x? It gets multiplied by 3, right? Then what's the next thing that happens? Added by 1. What's the next thing that happens? It gets square rooted. What's the next thing that happens? Divided by 4. What's the next thing that happens? Added by 7. Okay, so these are our steps. So what I'm going to go ahead and do is write that story of x. I'm going to go ahead and say, okay, the story of x was that I got multiplied by 3, and then I got added by 1, and then I got square rooted, and then I got divided by 4, and then I got added by 7. How did I do? Is that correct, that this was my story of x? Okay. So what you do when you solve algebra is you want to undo all those operations. You want to get rid of all of that extra material surrounding x, so that when you're done, you just have x equals. And what actually happens is all that structure reappears over here on the side of the 8. But you don't ever see that structure because you just do the simplifying as you go. So at this point, I think we all know what we would do. Since it's x is being multiplied by 3, adding 1, square root divided by 4, added by 7, you would subtract by 7. And so what I want you to notice is that to solve algebraically, we now work our way back up, going from the bottom to the top. And what do we do? The opposite of each one. So you actually do the opposite of each step in the reverse order, opposite in reverse. Okay, so let's do it. We're going to start here. I'm going to go ahead and subtract 7. So if I subtract 7 from both sides, I now just have root 3x plus 1 over 4 equals 1, and I'm done with that. Well, it was dividing by 4, so now I'm going to multiply by 4. So I multiply both sides by times 4. And so now that step is done, and I have root 3x plus 1 equals 4. And then still working my way up, the opposite of square rooting would be squaring, so I'm going to square both sides. And now I have 3x plus 1 equals 16. Now that step is done. So now, the opposite of adding 1 is subtracting 1. I'm subtracting 1 from both sides. That's 3x equals 15. Done with that step. And then the opposite of multiplying by 3 is dividing by 3. So I divide by 3, and I get x equals 5. And I'm done. Right. One more really fun way that you could think of it, that maybe you've never seen before, is if I took that same exact problem, 3x plus 1, 4 plus 7 equals 8. I want you to actually watch. I'm going to undress x, if you like, and put all those clothes on the 8. So I start by, I'm going to come over here, and I'm going to do 8 minus the 7 times the 4, square the whole thing, and then, let's see, I'm undressing it as I go. Subtract the 1, and then divide by the 3. There, I did it. I undressed x. Isn't that fun? I just shifted all those symbols over to the other side. That's kind of fun and clever and interesting. Now, of course, if you really did algebra that way, now you'd have to go back and actually solve all that, which normally you just do as you go. But if I did go ahead and solve all that now, a minus 7 is 1, 1 times 4 is 4, 4 squared is 16, 16 minus 1 is 15, 15 divided by 3 is 5. All right? Okay. The key thing here, other than enchainment, is to focus on the story of telling the story of x, and then going backwards in reverse order. So what I want to do then is do the antiderivative. So how do we do the antiderivative? What I'd like us to do is go ahead and tell how you do the regular derivative. So here's my regular function. We're going to do the power rule, x to the n. And tell me the derivative story. How do you do the actual derivative? What's the step for doing the derivative? What do you do first? You multiply by the exponent. Right, so that'd be step 1. You multiply, and this is the part you want to write down. Multiply by the exponent. Okay, so then I'm creating my derivative here. I just multiplied by n. And then what do? Subtract by 1. Well, there we go. Not nearly so long as the algebra problem that we tried. So just like algebra. Oh, there. So that's our power rule. So then, how would you do the antiderivative? Yeah, now remember, if this was how we did the derivative, we have to go opposite in reverse. So what would my first step be for the antiderivative? And we'd have to add 1 to that exponent. And then divide by what you get. You know, so whatever you just added 1 to, that new number that's bigger by 1, you divide by the result, by resulting exponent. And that's an antiderivative. So just like you now already memorized this one process for taking a derivative, where you multiply and then subtract one, now you have to learn the antiderivative process, which is add one, divide by what you get. Add one, divide by what you get. I'll just tell you right now, it's going to hurt your brain a little bit, and you're going to start doing them backwards. Maybe, you know, you have to, that's why you have to practice. You have to practice. You might want to like tattoo one of each on your hand, right? Like derivative, multiply by exponent, subtract one. Antiderivative, add one, divide by what you get. Like you want to have those steps out in front of you, because what you don't want to do is start doing them backwards and intermixed, because then you're just going to get sloppy, and it's going to be harder for your brain to remember the difference. So there's our antiderivative. So I'm going to write it over here so I have some room. Derivative was multiply, subtract 1. The antiderivative, which I'm going to use all my words, is add 1 to exponent, divide by what you get. That's just how I say it. You can feel free to say it any way you like. But that's the antiderivative. So let's try it once. Go ahead and write down what the, so over here, this is f of x equals x to the n. So the derivative would be n x to the n minus 1. So now watch what we're doing here. If I wanted to do the antiderivative, the integral means antiderivative, of x to the n, the answer would be, what do we do? Add 1, and then divide by what you get. Now that's one way to write it. You don't have to write it that way. That's just one way to write it. In fact, I never write it that way, but that's just literal. What I would do is I'd write x to the n plus 1, and then a fraction, 1 over n plus 1. That's the antiderivative. So we're doing the integral, the integral of x to the n dx. Let's do add 1 to the exponent and divide by what you get. But dividing by n plus 1 is the same as multiplying by the fraction 1 over n plus 1. And this is going to be easier for us, you know, just in terms of doing the advanced techniques for algebraic manipulation and simplification. It's easier if you make it a fraction instead of putting it in the denominator. So there we have it. That's an antiderivative. So let's try a couple. Everybody, we're on 3.2. We're going to do some antiderivatives. Now the fact is, this is a bigger problem than just the antiderivative. What we're going to do is practice doing the indefinite. So yeah, we're going to do both. Indefinite means you don't use the numbers and you just do the antiderivative. You say you're done. And then the definite is when you actually use the numbers. So let's just first practice the indefinite. So label it indefinite. Indefinite integral means you're just going to use the integral symbol to mean antiderivative. When you do the indefinite integral, there is no lower and upper limit. You're not actually calculating an area. You're simply doing the antiderivative. So let's try this. We're just going to do the antiderivative. And the step is add 1 to the exponent, divide by what you get. So I'm going to add 1 to the exponent. 3 plus 1 is 4. And then divide by what I get. I take the coefficient that's already there and divide it by what I got. Okay, so you notice that this coefficient 4, I bumped up in the numerator. And then I added 1 to the 3 and divided by what I got. This is a little confusing example because they're both 4s. But the nice thing is those 4s cancel out, and you end up with just 1 x to the 4th, or simply x to the 4th. So the antiderivative of 4x cubed is x to the 4th. How can we check our answer? Are we right? Yeah, now that I have this answer, I can just take the derivative and see what I get. So what is the derivative of x to the 4th? 4x cubed. Okay, well, wonderful. That closes the loop. Because derivatives and antiderivatives are reverses of each other. So if you do the correct antiderivative, you should be able to just check your work by just taking the derivative and check to see you get the same thing. So that's nice. Let's try another one. We're going to try, get my formula out of the way here. We're going to do the indefinite integral of just 3. Well, what's the antiderivative of 3? That might feel a little confusing. Where's the x? Where is the x? Where's the x?
Oh, it's
Yeah, it's really actually 0, right? You have to put that in yourself. It's interesting how much you have to think about invisible things. So there was an x there, it was actually 0. So now follow the steps. Add 1 to the exponent. So that'd be x to the 1. 0 plus 1 is 1. And then divide by what you get. So I shifted the 3 up into the numerator, and I divided by the resulting exponent, which is 3x. Now check your work. What's the derivative of 3x? 3. Right? So that worked. Now, if you don't mind, we're going to do I'm starting my work that I'm using the left-hand side, and then we're going to go back and use the right-hand side. Or maybe we'll just do the rest of the work on a separate sheet of paper. But let's go ahead and keep going and just keep practicing these indefinite. Oh, wait.
Quick question.
Yeah.
When you see the integral in the number dx means derivative of.
Dx technically means the dx. Delta x means a change in x, which originally came from the slope formula x2 minus x1. Delta means change, right? So delta means change. And so in English, not wanting to continue to write a triangle, it starts with d for delta. We write a dx, but now what they're referring to here is an infinitely small change. And what we're referring to here is a thinly sliced rectangle whose height is f of x and whose width is dx, which is assumed to be infinitely thin. Yeah. Because ultimately, remember, the long s means sum, and we're finding the sum of rectangles here. Rectangle is a base times a height. And each rectangle, the height is f of x, and the base is infinitely thin, dx. So that's really what the integral symbol represents. We're finding the sum of infinitely many rectangles. Yeah. Okay. Actually, you know what? That's fine, because I just noticed that number 3 and 4 are duplicate problems, right? Aren't they? They look somewhat duplicate. Oh no, I didn't update my screen. You have different problems. Okay, well that's fine. I just need to not put what I just have to change my problem. Everybody, how do you feel about the 2 indefinite ones we did? Okay. So we're going to continue doing the antiderivative, but now let's move on to your problems. So go ahead and flip to number, there we go. No, sorry, not that one. 3. Let me get another copy. Darn it. I'm so sad when I don't update my PowerPoint. There we go. Number 3. Number 3 says 5x. So your integral is the integral, let's just write down together the integral of 5x dx. I just want to practice the antiderivative a few times. So how would you do that integral? First of all, what would be helpful? To put a 1, right? Okay, so now, how do we do the antiderivative? The steps are? Add 1, so that'd be x to the 2. And divide by what you get. Okay, that's probably good. That's an antiderivative. Add 1, divide by what you get. Add 1, divide by what you get. We can do your number 4. What the heck? Since it's the last one. So your number 4 is the integral of negative 5x squared dx. So is the fact that the 5 is negative, does that mean anything to us? Not at all. We're still just going to do the steps. So what do we do? What's our first step? Add 1 to the exponent, so that's x cubed, and then divide by what you get. Okay, so there we go. Those are some nice simple practice problems of the antiderivative. Now we call that an indefinite integral. That's simply doing the antiderivative. It's the formula for the antiderivative. But now what we'd like to do is go back and let's actually compute some areas. Now to do the areas, there's a little bit more of an extra step involved. So we'll do all 4 of these to see how that works. Okay. Now first of all, notice I start you off at the very top with a formula, and it says the fundamental theorem of calculus. Does Does everyone have that on the page? Yeah. So the fundamental theorem of calculus, if you look, states that if you want to take the integral from a to b of some function, you'll notice that they write the function f prime of x because they're going to do the antiderivative, which would just be f. And what you do is, once you take the antiderivative, you plug in the top upper limit and you plug in the lower limit and you subtract what you get. So again, let's just look here. If your original function is f of x and you take the derivative to get f prime of x, then going this way would be the antiderivative. And that's why they start us off with the symbol f prime of x. Because they want to be able to say, hey, here's an integral of some function, and take the antiderivative, so to go backwards from the derivative to the original antiderivative, and then plug in the top number, plug in the bottom number, subtract. Okay, so let's try it. The very first problem, this is what everyone has, right? Yes, it is. Okay. Now, again, I realize that you already wrote some stuff down, so if you want to get a sheet of line paper out, or just if you have space, what we're going to do is work sideways. We're going to use up a whole line. So look for a space that you have. Okay, let's start the problem. We're doing the integral from 2 to 7 of 4x cubed dx. The first thing you do is just do the antiderivative like we did. So you would add 1, x to the 4th, divide by what you get, and then we're done with the antiderivative. We're done with the integral symbol, we're done with the dx symbol. We still need to notate the 2 and the 7. So what you do now is you draw a vertical line to the right of it, keeping the numbers 2 and 7. The vertical line is just a vertical line. It's not a long L, like this is a long S. It's just a line. And that line is just there as a placeholder, a reminder that, hey, we did have this lower limit and this upper limit, and don't forget to use those numbers. So now what we're going to do is clean that up. I have a fraction there, that's just a 1. So I'm going to clean it up. It's just x to the 4th, the vertical line, 2 to 7. So all I did right there is just clean up the fraction 4 before, which is 1, which I didn't even bother writing. I just left it as the invisible 1. Okay, so now the fundamental theorem of calculus states that you use that formula now, x to the 4th, and plug in the top number, plug in the bottom number, and subtract. So here's what I'd like everyone to do. You're always going to write parenthesis minus parenthesis to show that we're going to use this structure, something to the 4th, here and here, subtracting the 2. But in the first case, we plug in a 7, and in the second case, we plug in a 2. So notice, I'm going to use the structure of x to the 4th, which is really something to the 4th, something to the 4th. And I'm going to plug in the top number, 7, plug in the bottom number, 2. That's a lot of parentheses, and I might feel scared. But just try it. I want you to do something more comfortable to get with it. Yep, now we're done with that long vertical line, because that was just a placeholder to remind us that our upper limit was 7 and our lower limit was 2. And now we just compute that. So 7 to the 4th is a very big number. I mean, not very big. 2001. Minus 2 to the 4th, 16. And that gives us 2401 minus 16, 2, 3, 8, 5. What is that number? Very good. That's true. What does that number represent?
An area.
Yeah, the area. That is now actually the area. So if I go here and I draw this function for x cubed, and I look between 2 and 7, so if I look between 2 and 7, I have to make my graph really tall. There we go. So look between 2 and 7. That's what I'm looking for. I'll draw in some vertical lines so we can all see. Between 2 and 7. Oops. There we go. So I'm only looking between 2 and 7, and I'm wondering how much area is that? There we go. How much area is that? 2,385. So if I were to shade all that in right there, I'm saying that's how much area there is from 2 to 7 underneath the curve 4x cubed. So that's what we just found, just so you all know. So I would notate that number, 2,385. That's an area. Right? We don't know what units. It could be inches squared, feet squared. Square feet? Yeah. We don't know what the unit is, but we know that it's an area. Okay, very nice. Let's try another one. So we're going to do the integral -1 to 2 of the function 3, which we know is 3x to 0. So the first thing we do is the antiderivative. So you add 1, divide by what you get, and then draw your vertical line as a placeholder to keep your lower limit and your upper limit. Because that point right there where I added 1 and divided by what I got, I'm done with the integral. I'm done with calculus. At this point, the lower limit and the upper limit, those are kept there by this placeholder of a straight line to remind me to plug them in and subtract. So I'm going to clean that up. 3 over 1 is just 3, and x to 1 is just x. So it's 3x, placeholder, -1 to 2. So I don't know if this would help you, but this first step was calculus. The second step was cleanup. The third step is the fundamental theorem of calculus, where we do parenthesis minus parenthesis. That is the fundamental theorem of calculus. F of b minus f of a. It's two quantities being subtracted. Now I'm going to use the structure of 3x. That's 3 something, 3 something. And I'm going to plug in the top number, plug in the bottom number. And now it's just a matter of arithmetic. So this step is the fundamental theorem of calculus. And this last step is arithmetic. So what is that? 6, -3, 6 minus -3, which is 9. You know, if you really look at this, there's a lot of humor here. Okay? We're doing integral calculus. That sounds tricky, right? Like, woo, integral calculus. What's the first thing we do? We take an antiderivative. Okay, that's calculus, so now some heavy lifting. What's the next thing we did? Simplified the fraction 3 over 1. Got rid of the invisible 1. Okay, that's just cleaning up your algebra notation. Next thing we did? Fundamental theorem of calculus. Once again, sounding very impressive. Fundamental theorem of calculus. What's the last thing we did? Arithmetic. Right? What's the end of every integral problem? And it's almost, that's all there is to it. Okay, so what did we just find? We found the area. Everybody take a look at this graph. Apparently the area is 9. Let's see if we agree. My graph is the number 3. Number y equals 3. There's the graph. And we're going from what? -1 to what? -1 to 2. -1 to 2. So take a look at that shape. What is it? Square. It's a square. How tall is it? 3. How wide is it? And the area of a 3 by 3 square? No. Okay. Let's try a couple more. Now I have to update my screen so that it's the same problem that you're doing. Okay, I'll leave that there. Okay, the next problem is 5x. From -1 to 3. Oh, I don't need to mention. So -1, 3, 5x. Yes. Is that the problem everyone's about to do? Okay. So first of all, you remember on the x, I'm going to put a 1 there because I have to add 1 to it. So it's helpful to have a number there. So first step, do the antiderivative. So add 1, divide by what you get. And then vertical line, -1, 3. So that was the antiderivative. Right? Again, if you want to label your work, we just did the antiderivative. That's all we did. Is there any cleanup to do? Not really. I mean, we could replace 5/2 with 2.5 if you wanted to. That made you feel more comfortable, but 5/2 is fine. Okay, next step. Now we do fundamental theorem of calculus, FTOC. So we're going to do big parenthesis minus big parenthesis. We're going to use the structure 5/2 x squared. 5/2 something squared. 5/2 something squared. Notice that you use that structure twice. You're doing the structure of 5/2 x squared minus the structure of 5/2 x squared. And what are you plugging into those? The 3 There you go. And now what are we going to do? Arithmetic. So, let's see, 3 squared is 9, and the total is 45. 45 divided by 2 is 22.5. And minus, negative 1 squared is positive 1. 5 halves times 1 is just 5 halves. So that's 2.5. And 22.5 minus 2.5 is 1. Is our answer correct? All of you, we won't have time to do it today, but other than checking work on Desmos, you can do integrals on your TI-82 or TI-83. It's pretty nice. So what was that problem, 5x? Okay. Integral -1 to 3? Yeah. So 5x? The answer is 20. So it worked. And if we wanted to, we could just look at the graph 5x, and we could go from -1 to 3, which I would just have to change my scale a little bit. So from -1, I'm going to box this up a little bit. From -1, 3. And now we can actually see, those are just triangles, right? Can anybody see that? Where do I have to put this so you can all see it? Everyone see my triangles? Yeah, there we go. So look at those triangles. Just to take a geometric approach, I've got this teeny little fella, and I've got this bigger fella. And so that width is 1, and that height is 5. This width is 3, and that height is 15. So this triangle, 1/2 base times height is 2.5. Oh my gosh. And then this triangle up here, 3 times 15 is 45, divided by 2 is... Wasn't that cool? Wasn't that interesting? That it found the positive triangle up top and the negative triangle down below. That's not always going to happen. I'm as impressed as you that turned out that way. Okay. So the geometric approach helped us there. Which one are we on now? 4? Okay. So this is our last example of doing. Hey, now by the way, did you notice this, the arc, the storyline arc of calculus got worse before it got better? Right? So like antiderivative, fundamental theorem of calculus, arithmetic. Okay, last one is evaluate from 1 to 3 of -5 x squared. Yes. Now, before we even do this problem, I always encourage you to know what you're doing. Isn't that great advice? Know what you're doing before you do it. What does that shape look like? What are we looking at here? It's an upside down parabola. And where is it? Here. That's our upside down parabola. So note, what are we about to do? We're about to go from 1 to 3. So here's say 1, 2, 3. So we're going here to here. What are we about to find? That area. What should our area be? Negative. Okay, so that's a lot. We already know a lot. We know a lot so far. And plus, I can even find this point right here, because it's an upside down plot. If I plug in 3 squared is 9, 9 times 5 is 45. So this looks like a triangle with a height of 45 and a width of 2. If I were just to ballpark it, I would say 1/2 base times half height, 1/2 times base times height. My area is going to be roughly -45. You know, it's just off the cuff, right? If all I had was a napkin at a restaurant or I was at a party, I'd be like, hey, you know, -45. You know, just an answer you kind of throw away. So now let's do it. We do the antiderivative first. So first, the antiderivative. Add 1, divide by what you get. Does everyone get -5/3 x cubed? Keep the vertical line from 1 to 3. Oh, sure. Having a problem. Yeah. Okay, that was the antiderivative. Now we don't have anything to clean up. So we proceed to do the fundamental theorem of calculus. So now we have big parenthesis minus big parenthesis. It's always big parenthesis minus big parenthesis because that's the fundamental theorem of calculus. When you're subtracting two things. Now I put the structure, -5/3 x cubed, in each of them. So negative 5/3 something cubed, negative 5/3 something cubed. I like layering in my information like this. Parenthesis minus parenthesis, structure, structure. Now what do? Plug in the numbers. Oops, I did that backwards. Whoops. What would that have done to my answer if I switched them? It would have screwed it up, very good. Specifically, what would it have done?
Made your answer positive.
Very good, because if I was supposed to subtract 2 minus 7 to get a negative 5, but then I switch them and I did 7 minus 2, I would have got a positive 5. And I would have known and caught myself that I did that wrong, because I'm expecting a negative number. And had I left those switched, I would have gotten a positive number, and I would have said, wait a minute, hold on, I was supposed to get a negative number. Okay, so negative 5/3 times 3 to the third is 27. Minus negative 5/3. Now be really careful with your negatives as you're typing all of this in to your calculator. But again, we already know the answer should be negative, so that's helpful. Times 1. And I got the answer, negative 43.3. How was my armchair solution? Negative 45. No, not bad. Never happened. Now I know my phone went off. Did I already tell all of you that I was planning on playing a trick on you by changing the time on that clock and changing my phone so it'll go off like 15 minutes later? I bet you all would catch me because one of you would be phone. Okay, so what have we gotten to? This is really good progress. What have we found out today? We have found out, other than reviewing all that nice information about integrals and infinitely thin rectangles and adding them up and how to read the integral notation, we now understand an indefinite integral. I'm going to write this down somewhere. An indefinite integral, which is simply no upper and lower limit, versus a definite integral, which has a lower and upper limit. So what's the difference between these two things? An indefinite integral is just the antiderivative. That's it. You're just finding a formula for the antiderivative. So add 1, divide by what you get. The answer is 1/3 x cubed. It's a formula. All right, so that's the indefinite integral. You're simply doing the antiderivative, and it's just a formula. Which, if I take the derivative of that formula, it better give me back the original one, and I've checked my work. Whereas when I do a definite integral, that's because I do put in a lower and upper limit. That's because I am calculating an area, and I am actually shading something in. And therefore, when I'm done, I would actually have to use the fundamental theorem of calculus to actually compute something, which in this case would be 64/3 minus which is 21. So apparently my area here is 21. Okay. So in this case with the definite, you actually are computing an area. So that's a huge difference, right? The indefinite integral, you're finding a formula. With the definite integral, you're doing the fundamental theorem of calculus, and you're actually computing a number, which is the area. Will there ever be a variable over here? No, because it's an area. You're going to have an area, 2,000 square feet, 21 square feet, something like that. It's just a number. Area is just a number. Well, great. We've got a lot of theory under our belt here, folks. This is all very good. So let's see here. We got through 1 through 4. I'm really happy we introduced all of that. Oh yeah, and I didn't update this anyway, so everything's good. When you go home tonight, I expect you all to be completely done with more section 3.1 and to start more section 3.2. But 3.2 will not be due on Tuesday. All you have to do on Tuesday is 3.1. Any thoughts or questions? Oh, it's 12:48. Any thoughts or questions? We still have 2 minutes. Put what back up? Let's see. Your calculators. We do have 2 minutes. Would anyone like to know how to do an integral on your calculator? Or you're like, come on, Mr. G, let us out 1 minute early for once in your life. You've already started packing up. That's fine.
These shows have the.
Great, yes, I would love to. So on your calculator, we'll do a very simple one. You're going to go to y equals. Is it? Oh, okay, yeah. So you go to y equals and you type in what we just did the function negative 5x squared, right? So let's type in negative 5x squared. Okay, so we have negative 5x squared. Now go ahead and graph it. When you hit graph, you don't see the upside down parabola, well, you should. But if you don't, hit zoom standard. And zoom standard will give you a graph of the upside down parabola. So does everyone see the upside down parabola? Notice at this point we haven't done any calculus, we just graphed negative 5x squared. Okay, what you're gonna do is the button that says trace, don't hit trace, hit second trace. So you're going to the second trace above it is calc. So second trace, you have a list of options, value 0, min, max, intersect, dy dx, which is the derivative, and then you'll see option 7 is the little long s. You see the long s? Go down and choose the integral, the long s, says integral f of x dx, hit enter, and now it's going to give you two options, lower limit. Well, first it says lower limit. Right now you can just type the lower limit. You can type 1. That's the lower limit, you hit enter. Then it says upper limit. Our upper limit is 3. You type it, you hit 3, enter. And then you'll see your calculator actually shaded the area under the graph, and it actually shows you the shaded area in addition to just giving you the answer. So it's kind of a cool visual. Okay, now who needs help with that? Hey, you got it. Nicely done. Did you get them all? See you. See ya. True to form, 2 minutes, pass by time. Okay, so you have your function, very good. And now graph it. Oh, it says split. Oh, because your window range is a little long. Your window range has to go, well, first of all, you can always hit zoom standard.
Okay.
Zoom standard just puts you back to the normal left hand, right hand, up, 10, down. There's no upside down parabola. Now you hit second calc for second trace. And you go down to the integral option, that's the long s. And then the lower limit is 1, and the upper limit is 3.
Oh.
It's even the answer we thought, negative 43.3. I try to run class late so that none of you can ever come back and ask for a refund.